Hello, math analysis students. Today in this video we are going to learn about applications of exponential functions, and we're going to be talking about growth and decay. We're going to write and solve equations that model examples of exponential growth and decay. So to start off, we have any quantity that grows or decays by a fixed percent at regular intervals is said to have exponential growth or decay. And our formula for this is the formula is A equals P times 1 plus or minus R to the T power. Now that plus or minus depends whether it's a growth or a decay model. A stands for the future amount. P stands for the initial value, or if you would prefer, you could call it the principal value. It's the initial or the principal value. R stands for the rate. This is always a percent, and we always want to write this as a decimal. T stands for the amount of time, and if it's growth, then we will have 1 plus the rate of growth, and if it's decay, we will have 1 minus the rate of decay. Okay, so let's take a second and let's take a few examples and just determine whether each of the following equations represents growth or decay. I encourage you to pause the video, take a look at each, determine what you think they are, and then play again, because I'm going to go through them right now. So this first function right here, because we have a minus sign right here, that makes this function a decay function. Our second one, same thing, because it has, get the right highlighter here, because it has a minus sign right here, this makes it a decay function. Our third problem, now it doesn't say 1 plus anything or 1 minus anything, but 1.05 is 1 plus 0.05, therefore that means that this is increasing. This is a growth function. And our last two examples right here don't quite match the same model, but they're similar to each other. We have y equals 4.5 e to the 0.05 t, or y equals 2e to the negative 12t. Here we're looking at whether this exponent is a positive or a negative amount. Since this one right here is a positive amount, then this is a growth function. And since our bottom one right here, 2e to the negative 12t, since that's a negative, then this is a decay function. Okay, so now we're going to move into some word problems. Number one, the approximate number of fruit flies in an experimental population after t hours is given by q of t equals 20 e to the 0.03 t for times greater than 0. So first, does this represent growth or decay? Well, since this number up here is positive, then this is a growth function. Find the initial number of fruit flies in the population. Well, the initial number of fruit flies would be at the time when t equals 0, when no time has passed. So we would find that by evaluating q of 0 equals 20 e to the 0.03 times 0 power. Now when we have 0.03 to the 0 power, that's going to be 0. And 20 e to the 0 power, well, e to the 0 power is 1, so 20 times 1 is 20. So our initial population would be 20 fruit flies. Now, how large is the population of fruit flies after 48 hours? So 48 hours, this will be our t. So let's plug into our formula. Remember that our formula is q of t equals 20 e to the 0.03 t. So 48, we're looking for q of 48. That equals 20 e to the 0.03 times 48 power. We are definitely going to need our calculator for this. So first I'm going to show how to do this on the graphing calculator, and then I'm going to show how to do this on Desmos as well. All we have to put in is 20 e to the 0.03 times 48 power. So let's pull up the graphing calculator first. And in order to find E, we need to look around for it. E is over here on the right-hand side above the division key. And notice that it's in blue, so we need to press second. So second E. If we press that, I'm just going to click that right now, and it's not just a variable. E is that irrational number, 2.718. It keeps going, stands for Euler's number. So if we want to calculate 20 e to the 0.03 times 48 power, then we would type 20 for our e, second e, and we want to raise it to the power of, let's see, 0.03 times 48, and press enter, and we get 84.4. So that would be our answer for this. Let's go over and explore how we would enter that on Desmos also. So on Desmos, now Desmos has, if you want to find logs and natural logs, they're over here under the functions and miscellaneous, but there is not an E key anywhere on here. So for Desmos, you would need to go to your keyboard and hit E. And just to confirm, if we just type in E, it is that irrational number of 2.718, just the same as it was on the calculator. So if we wanted to calculate here on Desmos 20 e to the 0.03 times 48, then we would enter in 20, and remember, go to the keyboard to get E, to the power of, let's go ahead and put it in parentheses here, 0.03 times 48, and we get that same result, 84.4. So going back over to our note sheet, this gives us about 84.4, or in practical terms, that's about 84 fruit flies. Okay, let's move on to another example. When doctors prescribe medicine, they must consider how much the drug's effectiveness will decrease as time passes. An adult takes 400 milligrams of ibuprofen. Each hour, the amount of ibuprofen in the person's system decreases by about 29%. How much ibuprofen is left after 6 hours? Okay, so we're going to use our function A equals P times 1 minus R to the t power, because we know that the effectiveness is decreasing and the amount of ibuprofen in the person's system decreases. So these words decrease indicate that we have a decay function. So I'm going to list all of my values over here. You don't have to do that, but A, that's the amount. That's what we are trying to find. P, that's the initial or the principal amount. They took 400 milligrams of ibuprofen, so that's our P. And our R value is 29%. Remember, we want to write that as a decimal, so 0.29. And T, how much ibuprofen is left after 6 hours, so T is 6. So we'll plug our numbers into our formula. A equals 400 times 1 minus 0.29 to the 6th power. Then we can either go over to our graphing calculator if you have one, or you can go over to Desmos, enter in, and if we get to 400 times 1 minus 0.29 to the 6th, we get 51.24 milligrams for our final answer. That's how much would be left after 6 hours. Let's do one more example here. This equation describes how a population of bacteria grows. A equals P e to the 0.107 t. P represents the initial amount of bacteria. The variable A represents the amount of bacteria after time t measured in hours. How long would it take for a colony beginning with 500 bacteria to double in size? So I like to list what my variables stand for. A, that's the amount right here. Well, if it's going to double, if it was 500, then our final amount is going to be 1,000. Our P was our initial amount. It was 500. we don't have an R here because this is describing it, but our t in time, how long would it take? That is what we are trying to find. We're trying to solve for t here. So we need to plug these numbers into our equation. So a equals p e to the 0.107t. And we're solving for t, which is in the exponent. So first we need to try to get rid of these other things. Well, we've got 500,000. Let's go ahead and divide by 500. That gives us 2 equals e to the 0.107t, which makes sense because how long will it take for it to double? So then we want to get this t by itself, but it's in the exponent. So we need to get rid of this base of e. How do we get rid of the base of e? Take the natural log of both sides. If we take the natural log of 2 and the natural log of e to the 0.107t, well, the natural log and e cancel each other out because remember that the base of our natural log is e. So when e is the base of our log and the base of our exponent, they cancel. So the natural log of 2 equals 0.107t. Now to get that t by itself, we just need to divide by the 0.107. And then we get that t is equal to the natural log of 2 over 0.107. Well, we'd really like to get that as a decimal, so if you go over to your graphing calculator or go over to Desmos and enter that, the natural log of 2, divide it by 0.107. Let's make sure to do that on the calculator. I'm just going to show really quickly. The natural log, remember on your graphing calculator, is over here on the left. The natural log of 2, close your parentheses, divided by 0.107, enter, gives us a value of 6.48. If we went over to Desmos to calculate that same thing, if we entered the natural log, which is under functions, under miscellaneous, there's our natural log of 2, close parentheses, divide by 0.107, then we get that same answer right there, about 6.48. So when we come back to our answer, then we're asked how long would it take for a colony of bacteria beginning with 500 to double in size. Then our answer would be that would take about 6.5 hours. And that is how we solve exponential equations. Bring questions with you to our next class. Okay, bye-bye.